Assalamualaikum. Hmm, ini after the revision, development of processes involving class changes, general procedure, and I think in engineering analysis with which component is in two phases, you must choose a reference state for that component by specifying both a phase and a temperature and calculate the specific enthalpy of the component in all process. Stream relative to this state. If the substance is a liquid at its reference state, and vapor in the process stream enthalpy may be calculated as outlined in section 8.4a recited to the book. That is, bring the liquid from the reference temperature to a point at which delta Hb, that is it my ah oh yes. Delta Hb, sheet of vaporization. That one is for if the first the initial state is liquid, and you need and it changes to vapor, so you need to raise the temperature to heat of vaporization. It's in appendix B, page 638. Bring the vaporized is non-vaporized liquid. So the temperature that you raise is until the TB, boiling point temperature, in which the liquid turn to vapor. So meaning reference initial, where is it? Bring the liquid from the reference temperature to a point at which, okay. So reference temperature to TB or boiling point, then delta Hb plus delta Hb, then plus from TB to the process stream temperature. Bring the vapor to the process stream. Some random interpret change for the three step. Yeah. Like this lah. Yeah. From liquid to vapor, then yeah, the process temperature. Yes. So yes. Let's see. Yeah, example for an equimolar liquid mixture of benzene and toluene at 10 degrees C is fed continuously to a vessel in which a mixture is heated to 50 degrees C. The liquid product is a 3 mole percent B is benzene. The vapor product is 68.4 mole percent benzene. How much heat must be transferred to the mixture per gram mole heat? So basis in this case is 1 mole, so it's equimolar, meaning 50-50, so 0.5 mole benzene over mole of this. Then we have vapor go up, liquid go down. So in vapor form, okay, vapor product of B is 68.4, so 0.684. So the rest is toluene. So 1 minus 0.684 is 11316. The same as this. Yeah, 40% B for the liquid form. Do the mass balance like this. So 1 mole. It depends on your basis. If you choose 1 mole, it's 1 mole. If you choose 1,000 mole, in this case is mole, equimolar. You choose mole. See, mole again. Mole percent. No need to change to see, weight, kilogram, gram. Let's use mole. Do the mass balance. This is total mass balance 1 mole in NV and plus NL here. Then this is mole, sorry, balance for benzene. You can also use toluene, no problem. It's the same, but choose one only. Then NV and NL is this. NV, don't forget to write the reference. This is the reference. 10 degrees, okay. 10 degrees here. Based on the feed. So at reference point, no enthalpy here because it's same temperature, so 0. But there's still a mole for the balance, S balance, this S balance. So only calculate for H1, H2, H3. But see the form here. BL refer to liquid, benzene. BV refer to the vapor, benzene. T is toluene, liquid and vapor. Don't forget to write the table. The value of an output heat capacity, latent heat data needed to calculate enthalpy obtained from table B1 and B2. So data table B1, B2 is in the appendix, page 628 in the book. The formula okay, given below. So you need to do this. They skip some part, lot of part, but you need to do. Let's do the integration. So CP here from 0, sorry, from 10 to 50. You refer back to the table. Temperature reference is 10. So for H1 is benzene in liquid form, so the phase is not changed. So meaning you can just find CP. CP, go to table B2. Table B2, page 635. There are two states, so you choose liquid. because this is liquid. Yeah. So plug in the value 126.5 times 10 to the power of negative 3. Although in the table is 10 to the power of 3, if you write it, it is negative 3 T. Refer to the form. In this case, for benzene, only form 1. So you see the table capacity up there, Cp equal to A plus Bt plus Ct square plus Dt cube. So in this case, for benzene, only 2, A and B. So you need to integrate to T and plug in this value, meaning 50 minus 10. And you get, you do it, make sure you get this value. Similar to H2, H2 is toluene in liquid form. So for toluene in liquid form, you need to refer to table B2 still, but page 637. Similar, this is in liquid form, so you need to choose the L or liquid form 1 as well. Only A and B. Yeah. Do the integration. So this one is 50 minus 10. Okay, for H3 there are form changes, so phase changes from liquid to vapor. So what we do is, this is the initial temperature, then the 80.1, where does this value come? Is from table B1. Table B1, you search for boiling point TB. Because delta HV here, this delta HV, or heat of vaporization, meaning you want to change for a phase from liquid to vapor, you need delta HV. So delta HV occurs at, sorry, vaporization of benzene occurs at 80.1 degrees C. That's why we increase the values here from 10 to 80.1. So at 10 to 80.1, there are CP. So CP here refer back to table B2. Table B2, page 635. This is for liquid. Yeah. So don't copy from here. You need to redo it again because the temperature is different. You can still use the integration, but the plug-in, meaning this is 80.1 minus 10 now. Delta HV, you need the number from the table B1 at page 628 is 30.765 kilojoule per mole. Just plug in there. Plus, this is what they say, to reduce or increase the temperature from delta HV to the process temperature. So in this case, the process temperature here, this is the process temperature from 10 to 50. So meaning from 80, which is the delta HV, need to reduce to 50 the process temperature. Refer to CP here. So in this case, CP still need to refer to table B2, but in this case, it's in vapor form or in gas form. So you need to choose gas in the, you need to choose set G. L for liquid, G for gas, C for crystal. So in this case, gas or vapor is G. Then you choose the second one. So the difference between liquid and gas form for benzene is the amount of numbers for the A, B, C, and D. For the form, when you do the heat capacity integration. So you need to do this, then see did you get the same value or not. The same thing for H4 here. H4 is for toluene. So for toluene, refer table B1. Table B1 page 634. So the boiling point for toluene is 110.62. Meanwhile, the delta HV here is 33.47 kilojoule per mole. The same thing for this. This is for liquid. So you need to do the integration, but you need to choose a state liquid. And for this case, 1110 reduced to 50. This is a process temperature. This is in vapor form. You need to choose the gas form. The difference is liquid, they are shorter. For vapor, for heat capacity that you need to integrate is longer. Yeah, at least some until D, the form, the equation. Then once you obtain all, then just put in this equation. So n here refer back to this table. In this case, h in is 0. So meaning summation of this equal to Q. Don't forget to multiply with mole. This is the mole. Then you get, you see the unit without mole, 17.7 kilojoule. So you try this exercise. The principle is the same. The principle is the same. You see here that the liquid stream contain 50% benzene. The balance is toluene, so meaning 50-50. Temperature feed is 25. Oh yeah. Okay, fed the cleanliness station. So in this case, it they give the rate of feed. No need to do basis now. Half of it is benzene, half of it is toluene. Liquid vapor steam within the evaporator of at 25 degrees C. Don't forget to draw this block diagram in and out. The liquid contain this much, liquid contain this much, similar to this. Not similar in number, but similar how it's look like when you do it. So calculate the H. All right. So if you choose the reference point to be 25 degrees C, which is the feed, meaning the H in is 0 automatically. Yeah. All right. Energy balance, that one is energy balance for non-reactive. This is energy balance for reactive. So to perform energy balance on a reactive system, proceed as much as you did for non-reactive. Similar idea, the way you do it, similar. Just that this is there are reaction involved. To draw label, of course, do the metal balance, choose the reference state, calculate delta H. The method akan used to choose reference state for enthalpy calculation and to calculate specific enthalpy and delta H. The approaches will be highlighted in this course using a propane combustion process as shown in figure 1. Propane combustion, oxygen, nitrogen goes in, do the combustion, produce oxygen, nitrogen. This is the excess. Then propane tend to CO2 and H2O. Okay. The material validation for the illustrative and form and the represented into the flow chart. The propane version process kinetic diagram is this, the HR. Propane plus oxygen turn to carbon dioxide and water, delta heat of reaction is -2220 kilojoule. All right. First step, do the metal balance. Next is metal balance measurement method to get the system possible. The best choice are generally reactant and products at 25 degrees C and in the state for which the heat reaction is known. In the example process, and non-reactive is used at any convenient temperatures such as the inlet or upload temperature or the reference temperature used for the species in available enthalpy table. You can see in the first step for table B8. Table B8 is 8. Table B8 is at 25 degrees C 118. That's why they choose the best choice is 25 degrees C 180 because of the table B8. You can just choose for CO. There are, for example, for hydrogen, there are specific enthalpy for each temperature from 0 to 15, 1500. Mana punya tu? Degree C, yes, degree C. For single reaction equivalence process, calculate the extent of reaction. So to calculate the extent of reaction, refer back to this diagram. Yeah. See here, extent of reaction for propane. Yeah. So out is 0. No propane here. No propane here. But there are propane going into, which is 100. So out minus in over 1 mole per second. 1 mole, this one. 1 mole per second. Based on the stoichiometric. Satu. Oxygen is 5. Okay, then you get 100 of extent of friction. Prepare the inlet outlet enthalpy table. Don't forget to write the reference. Inserting non-molar. This is there are two methods. This is the first method, heat of reaction method. Inserting non-molar amount and I of low rate all inlet and outlet stream component. If any of the component is at its reference state, insert 0 for the corresponding HI. For example, the table would appear as follows. So this is the diagram, the block diagram. Inlet for propane, because this is happen at the reference temperature, which is here, 25 degrees C. So delta H in for propane is 0. Oxygen, nitrogen, carbon dioxide, and water. So for N in, this is for oxygen is 600 here. 2256 nitrogen, so H2H3. Same then for H out. So how many? 5. Oh, sorry, 6. Enthalpy itu calculate. Calculate each non-temperature component enthalpy. H for the species. Going from in reference state to the process state, insert the enthalpies in the table. In the example, H2 is for oxygen. So for oxygen, from 25 degrees C to 300 degrees C. See, 25 degrees C is the reference, but the temperature of oxygen going into the furnace is 300 degrees C. So you need to calculate it. Because you choose the reference state at 25 degrees C, meaning you can just choose the enthalpy, specific enthalpy for oxygen at 300 degrees C from table B8. Yeah. Oxygen 300 degrees C, table B8 is 8.47 kilojoule per mole. Yeah. So what happened is the temperature is let's say 250. There are no value in 250. So meaning you need to do the interpolation between 200 and 300. You proceed in the same manner to calculate H3, H3, H3. H3 is nitrogen. So nitrogen is also included in the table B8. For 300 degrees C, you see here, because this is 25 is the reference, need to find nitrogen at 300 degrees C. So refer to table B8, 300 degrees C, 8.12. Yeah. H4, H4, H4. Hey, the same with H4 here. H4 is at 1000 degrees C. So 25 to 1000 degrees C. 1000 degrees C is for oxygen is 32.47 kilojoule. H5 is nitrogen at 1000 degrees C. 30.56. What else? Carbon dioxide 1000 degrees C as well is 48.6. H7 is water. Water is also included in table B8. Yeah. It's 1000 degrees C, 37.69. Wait. H7 is at 1.71 kilojoule. Someone consider the last result by definition H7. This is calculation for H7. So for H7, there are phase changes here. H3, H4, H5, H6 is all in gas. Gas in, gas out. You see? Yeah. So for water at 25 degrees C, 25 degrees C, it's liquid. Yeah. Because the reference temperature at 25 degrees C. And 1 at the end. Don't forget. So this is liquid. We need H2O at 1000 degrees C. So in this case, from 25 to 100. So this method is for, you refer back to the non-reactive method, the same. So in this case, this one is refer back to table B1 to get the boiling point of water, which is 100 degrees C. Then N delta HV, for water page 634 is 40.656. So from 25, the reference temperature goes to the boiling point. So CPL, if you see the CPL, meaning you need to refer to table V2 for water. For table V2 for water, CPL refer to CP for liquid. So meaning you need to choose the form L. Yeah, form liquid form. In this case, only one value for water. Yeah, easy. Then this one is from 100 to 1000. Why 1000? Because of the temperature here. Process temperature is 1000. That's why we increase to 1000. So this one is CPV. CPV and CPL is different. So for CPV, you need to choose the gaseous form for water. It's a lot, like 33.46 A, 0.68880. This one for B, this is C and D. Yeah. Done, then you get value of 81.71 kilojoule. per mole. Why you cannot use table B8? Because of the changes in form. At 25 degrees C, 180 m water present at this reference point is liquid. But in this process, the water is in vapor or gas form. That's why you need to do all of these. Calculate the delta H. Delta H, extent of reaction. This is delta HR. Delta HR is given. That's why you choose the heat of reaction method, because delta HR is given. For extent of reaction, you need to calculate the extent of reaction. And this one is N out, H out, and in H in. This one is refer to the table. This table. Yeah. In this case, H in is not zero. Only propane is zero. Oxygen and nitrogen is there. See, H2, H3. Multiply these two value, then you put here. Yeah. Only this is can understand this. The see the value kilojoule per second. Why kilojoule per second? Because of the N in. N in is mole per second. That's why kilojoule per second. Okay. This is the heat of formation method. Similar example, but using another method. Heat of reaction, heat of formation. Okay, the similar thing, do the metal balance. How to do the metal balance? Refer to the non-reactive. Choose the reference state. In this case, it's 25 degrees C, 180 m. The choice should be elemental species. This is a heat of formation. They constitute the reactant and product in the state in which the movement are found at. 25 degrees C and 180 m. Non-reactive species at any convenient temperature. In example, the reference will be CS H2O2 at 25 degrees C. The elemental S is solid. The elemental species constituting the reactant product and nitrogen at 25 degrees C. The reference temperature of table B8. Table B8. Why you choose 25 degrees C and 180 m? Because of table B8. Prepare the, okay, this is the table. Don't forget to write the reference. The way you write the reference for heat of formation and heat of reaction is different. I see the difference. But the reference point is the same, 25 degrees C and 180. Why? Because of table B8, easy to do if you choose this reference point. All right, for this case, propane, because the reference doesn't have propane, because it's a species, heat of formation now. Since there are no propane as the reference, so propane cannot be zero now. Although it's appear here, it's inlet condition is 25 degrees C, 180 m, but it cannot be the reference point. So 100, okay, this one is similar. So in this case, you have 7 enthalpy you need to determine. If you see the heat of reaction, only 6. All right, for the reaction, products start with elemental species at 20 degrees C and 180 m. The reference and form 1 mole of the species at 20 degrees C and 180 m. Delta H to delta HF from table B1. So delta H equal to delta HF, table B1. So table B1, delta HF is the second last column. Second last column. When bring the species from 25 degrees C to the process state, calculating delta H using appropriate heat capacity from table B2. Specific enthalpy from table B8 or B9 and latent heat from table B1. The specific enthalpy that goes in the outer table is the sum of the enthalpy changes for each step in the process path. In the example, we will choose calculate the specificity of the entering propane H1. You see propane, this is propane C3H8. So 3C plus 4H2. You see the reference CH2O2N2. You cannot use CHON because the smaller species for hydrogen is H2. This is the oxygen. Oxygen is O2, not O. Nitrogen gas is N2, not N. So here 3C4H2 is equal to C3H8G gas. Yeah. Then delta H1 is HF equal to propane W1 propane wait, yeah, okay, tapi propane, this is enthalpy of propane at 25 degrees C. Yeah. Relative to C and Hg at 25 degrees C. If the propane had entered at a temperature other than 25 degrees C, a term of the form, this form, 25 to T naught would be added to the heat of formation of propane. Okay. All right. Next, we calculate the specific enthalpy oxygen at 300 degrees C, the process state, relative to oxygen at 25 degrees C, the reference state, S delta H2 equal to 8.47 kilojoule per mole. 8.47 kilojoule per mole refer to delta H2 at 300 degrees C. There is no heat of formation term since oxygen is an elemental species. This is elemental species. The what? The smallest. We proceed in the same manner to calculate H3, H4, H5, H6. So for H3 is, what is H3? H3 is oxygen at 300 degrees C at 0.12. For H4 is oxygen at 1000 degrees C, 32.47. H5 is, what is H5? Nitrogen. Nitrogen at 1000 degrees C is 30.56. For H6, CO2 at CO2 and CO2, sorry, for H6 and H7, H6 is CO2, H7 is water. So CO2 is different, H7 is different. To calculate H6 and H7, we form the corresponding species CO2 and H2O vapor at infinity C from their element delta HX, then heat them up from 35 to 1000 degrees C. Delta H equal to H1000 from table B8 and add the formation and heating term. So, okay. Heat of formation. Wait. Oops. Heat of formation for, let's say, CO2. Carbon dioxide. Carbon dioxide, CO2, HF. Apa ya? Salah, itu HF belakang. Liquid ke gas? Gas. Negatif 393. 393.5. 6G. Then 25 to 1000 degrees C. CO2 formation. Do you know why it heat formation? Because it formed. Because we talking about formation. You see CO2 here, it's CNO. So meaning one C plus one oxygen equal to CO2, forming CO2. That's why we do. It's different. We cannot just choose table B8. Different thing from O2 and oxygen. Sorry, oxygen and nitrogen. It's already the elemental species. There are no O plus O. The lowest form is the oxygen and nitrogen. Different with CO2 and H2O. That's why we need to do the heat of formation with 25 to 1000 degrees C. 25 to 1000. Degrees C. Yeah. So, so, oh, siapa yang nak ambil tu? You follow this, huh? So first you go to, for this H6 and H7, for H6, let's say H6, we do for carbon dioxide. Why you need to do formation? Because C plus oxygen become CO2. Although that reaction is not that correct, but that is what it is, the heat of formation. Okay. CO2. CO2 is page 629. You search for the second last column. There are two forms here. They are liquid and gaseous form of CO2. So for heat of formation, for CO2 is negative 393.5. Okay, write that one. Now, the temperature is from 25 to 1000 degrees C. 25 is the reference state, 1000 is the process temperature. So the process temperature is 1000, so you need to refer to table B8. So for table B8, CO2 at 1000 degrees C is 48.6. So negative 393.5, which is the delta HF for the CO2, plus specific enthalpy of CO2 at 1000 degrees C, which is 48.6, you will get negative 344.9. I do the same for water. For both circle, for both single. Okay, this is the delta H. Don't forget to multiply N and H out. Where is N and H out? This table. H is what you calculate. N is what you calculate from the mass balance. Or given. Depend. heat operation uniquely when the heat operation of the reactor and static members and other. I think the value and H the value needed at the H equal to 1.26 into 5 meter per second. Sama, ni tadi lah. 1.26 10 to 30 meter per second. Jadi 1.26 10 meter per second. Sama. Yeah. Although it is without the HR, if you refer back to the heat of heat of reaction, you will see extent of reaction times delta HR heat of reaction plus this form this K. The process file correspond to the heat of reaction is as shown below. Okay, this is the breakdown. The heat of reaction method amount to bring the reactant from the inlet condition to their reference state. A 25 degrees. Carrying out the reaction at 25 degrees C. Okay. So question delta H equal to extent of reaction time delta HR. The summation of such term from the production, meaning the product from the reference state at 25 degrees C to the outlet state, and summing the enthalpy changes for 3 steps to calculate the reaction for the ongoing process. This is heat of formation. You see the difference. The one extra. The heat of formation method amount to bring return. You see the arrow as well. It's from element to return end product. That's why you see the delta HF, heat of formation. For anything other than elemental species, you need to do the heat of reaction. Sorry, heat of formation. Okay. All right. So when to choose which one? Heat of formation, you can choose. Yeah. Whether the question got delta HR or not, you can choose the heat of formation. It is universal. But if you want to use delta HR, sorry, heat of reaction method, the first method, the question must give you that delta HR. Then you can use delta HR, calculate the extent of reaction and everything. Yeah. For me, it's easier to do heat of reaction, although you need to calculate more enthalpy. Right? Yeah. But if you choose delta heat of reaction, meaning you can actually because of the different state, one of the enthalpy is 0. Example, 100 mole mm, 100 about an ammonia oxidizer, 100 mole ammonia per second and 200 mole oxygen per second at 25 degrees C are fed into a reactor in which ammonia is completely consumed, meaning If you have that reactor, ammonia go in, no ammonia go out. The product gas emerge at 300 degrees C. Calculate the rate at which it must be transferred to or from the reactor, assuming pressure at 1 atm. The standard heat of reaction for the oxidation of ammonia is given below. So 4 mole of ammonia gas plus 5 mole of oxygen, becoming 4 nitrogen oxide plus 6 of water. The HR is negative 904.7 kilojoule, or this is the rate with kg per second. This is the block diagram. 100 mole, 200 mole, which is here, goes into the reactor. Go out is nitrogen oxide of water and oxygen only. Ammonia is completely assumed, consumed. Since only one reaction declares that the HR is known, we use the heat of reaction method. Because of that, the HR is known. But you can also use heat of formation method, regardless of the HR or not. Using as a reference the reactant and products within the state for which the heat of reaction is given. Don't forget to write the reference. The reference for heat of formation and heat of reaction is not the same. This is reference for heat of reaction. You see, it is not in elemental species. Although this one is elemental species, but what to do? It's an oxygen. Yeah. So this is not elemental species. This is not elemental species. This is not elemental species. For elemental species, it should be N2 here. H2O2. What is C? C. Oh, CH2O2 N2. Reference condition 25 degrees C, 1 atm. So write the table. This is the table. N in 1 per second. If the question asking you about using mole per second, don't need to change to kg. Just use mole. Easy. Yeah. Less error. This one is H in. Why 0? Because of the reference temperature. You need to calculate H1, H2, H3. And in and out here, normally you need to do the mass balance. If the question didn't give you the value. How to do the mass balance? Refer to the non-reactive. How they do the mass balance. Okay, H1, H2, H3, calculate the unknown enthalpy. So from table B8, H1 is equal to 8.47, 300 degrees C, oxygen. H1 is H out for oxygen. For NO here, nitrous oxide gas. Table B8. There are no table B8 for NO, so you need to use the normal method, traditional method. Using the table B2, because there are no phase changes, gas to gas. So yeah. Table nitrous oxide. So table B2. If you see CP, then automatically go to table B2. Yeah. B2. NO nitric oxide. See here, nitric oxide namanya. Nitric oxide got only one form here. Yeah, only one form, gas form. So in this case, only one form. Form one, the equation. Form one. Do the integration with from 25 to 300 degrees C. So this one is 300 minus 25 degrees. Atas solat yang bawah, saya H2O from table D8. Okay. Calculate the extent of reaction. Extent of reaction. You see here how to do. This is the mole. 4. Bawah ni. N is the how much is entered. Yeah. So N out minus N in here should be. In this case, 100. 100 lah. Wait. 100. 100 lah. Patut. Ammonia. Yeah, 100. So saya dah masuk. Sorry. There are no ammonia is completely consumed. So N out set, no N out. So 100 over 4, 25. This is the extent of reaction. Delta H, so extent of reaction delta HR is given -4.7 kJ per second. 25 is the extent of reaction. Calculate here based on ammonia. Can you use oxygen? Yes, can as well. No problem. You will get 25 as well. Should be sama lah. 75. Okay, where to get this? From table. From table, this table. What else? With HF negative 19,700 kilojoule per second. So the Q is equal to delta H, negative 19,700 kilojoule per second or kilowatt. 1,700 kilowatt of heat must be transferred from the reactor to maintain the product temperature at 300 degrees C. If less heat were transferred, more of the heat of reaction would go into the reaction mixture and the output temperature would increase. Okay. This is example for heat of formation. In the Milan or methane oxidation reactor, methane is oxidized with A to produce formaldehyde in a continuous reactor. A competing reaction is the combustion of methane to form CO2. So CH4 methane gas react with oxygen, become HCHO. Ayo, macam formaldehyde. Macam formaldehyde ke sini ya. HCHO. Sama formaldehyde. Wait. Formaldehyde tu lah. Formaldehyde. HCHO. Water vapor CH4 plus 2 oxygen. So competing reaction conversion of methane to form CO2, 2 oxygen become carbon dioxide and 2 mole of water. The flowchart of the process for an assumed basis of 100 mole of methane fed to the reactor is shown here. All species are gases. So for the heat of formation, the way you write the reference is like this. C is oxygen. This is an elemental species. Carbon in solid form, oxygen, nitrogen at 25 degrees C and 1 atm. So 9 enthalpy need to calculate in this question. H1. This is C plus 4, sorry, 2 H hydrogen. So it's a formation. You see here? Formation. Because it's occur at 25 degrees C, so no need for this thing. Just search for delta HF for methane. Page 631. There are only one form, gas, which is negative 74.85 kilojoule per mole. For oxygen, H2, so H2, HO2, 100 degrees C. So this one you need to refer to table B8. Because oxygen is the elemental species, so doesn't need to find the delta HF. So 100 degrees C, oxygen 2.24. Yeah, so tepat juga. 2.235. For nitrogen 100 degrees C, 2.19. Yeah, same. For methane again. Methane H4 here, outlet. Temperature wise, 150 degrees C. So 150 degrees C. So the first one, because this is delta H, so this is a formation C plus 2H2. So you need to find the formation, which is negative 74.85 plus from 25 to process temperature. 25 different, 150 process. CP got from table B2, which is 4.9 here. But you need to do it yourself. Confirm it. 4.9 is the value. Then you plus these two, get negative 69.95 kilojoule per mole. For oxygen at 150 degrees C, because this is elemental species, this is H5. Just choose from table B8. Nitrogen elemental species, H6. Go to table B5. For formaldehyde, formaldehyde is 1C plus 2H, sorry, 1C plus 1H2 plus half oxygen equal to HCHO. So this is a formation as well. Go to table D1 first. Heat of formation. Formaldehyde. Page 630. Negative 115. See negative 115. This is 25 to 150. This is table B2. Do the integration. What is the form? Tak tahu. Form for HCHO is gas. You see gas. So make sure you choose the correct the correct CP. If it gas, you choose gas. Because liquid is shorter, gas is longer CP. You need to integrate. How about CO2 is also formation. C1C plus 1 oxygen becomes CO2. So HF, this one is HCO. Because CO2 is inside table B8 at 150 degrees C, you can choose from table B8 directly. No need to do CP like this. H2O. H2O is heat of formation because 1H2 plus half oxygen. Okay, this is table B1 shape. This is table B8. So all of it, write it back in this table. Oh, that is okay. Then do this. Yeah, delta H. Okay. I think it's complete. Yeah. I hope you can answer the final exam. It's two questions each, 25 sorry, 25 marks. You need to answer both. Then they given there are some two rubric for each. Sorry, one rubric for each question. Written answer as well for explanation. Yeah, focus on this topic lah that we cover today. I cover today and do this exercise. So thank you. All the best.